Hello. We are now in chapter 2. This section has to do with complex numbers. And when you first learn about complex numbers, or you hear about complex numbers, and you think there's an I and those things right there, it takes a little while to understand why we are discussing them. And sometimes it's not until much later in mathematics when you see the beauty of it. But there's a whole course in graduate school called complex analysis that builds on this idea, and there are programs like NASA that will actually use this concept. Here we just kind of learn about the introductory part of it and how to manipulate terms dealing with the complex numbers. Alrighty, so that's kind of the prelim on this. And so on this actual section, we're going to have these learning objectives. We're going to talk about adding and subtracting complex numbers. We're going to talk about multiplying complex numbers. We're going to divide complex numbers. We're going to perform operations with square roots of negative numbers. And we're going to solve quadratic equations with the complex imaginary solutions. Alrighty, and that's going to require the quadratic formula. Alrighty, so let's begin by what is a complex number and the imaginary numbers. Well, the imaginary unit, which is I, is defined to be the square root of -1. So I equals square root of -1 is called the imaginary unit. So therefore, if you square both sides of that equation, you get I squared equals the square root of a -1 squared, which happens to be -1. So therefore, I squared equals -1. So, and that latter part, I squared equals -1, is going to be coming in handy when you're multiplying and dividing complex numbers. So that's just something you're going to have to kind of go to bring to memory banks and just say, okay, I squared is a formula that equals -1. So when you see one, you can replace it with -1. So I squared equals -1. Okay, and the set of all complex numbers are in the form a plus bi, all right, where a and b are real numbers and I is the imaginary unit. It's called the complex numbers. A lot of people get mixed up. They'll call the imaginary numbers and the complex numbers the same number system. And it's very common that people think of it that way, but it's not that way, okay? You have the imaginary unit. If you take the imaginary unit and multiply it by b, some real number like 2i, -5i, or 2/3 I, that is an imaginary number. Okay, when you add a real number like 5 or 7, in other words, a number without the I, and so here they're illustrating that with the letter A. So you're adding a real number to an imaginary number. So A is the real number, BI is the imaginary number. When you add them and combine those together, you get a complex number. But like I said, some people just kind of put them all in the same bowl. They'll just say, imaginary numbers, complex numbers, it's all the same. That's not really technically true. Okay, just the imaginary numbers like 2i, 3i, 5i, and then if you take a real number like 1, so if you get 1 plus 3i, 1 is a real number, 3i is an imaginary number, but when you combine them, you can't add them up because they're not like terms, so 1 plus 3i is a complex number. Okay, so the standard form of a complex number is a plus bi, a being real, bi being the imaginary number. Okay, so operations of complex numbers. So right now what we're going to do is learn how to add, subtract, multiply, and divide complex numbers. That's the main part of this this section. Okay, so the form of complex numbers a plus bi is like the binomial a plus bx. To add, subtract, and multiply complex numbers, we use the same methods that we use for the binomials. Alrighty? So, example 1, adding and subtracting complex numbers. So we're going to perform the indicated operations, writing the result in standard form. So if we have 5 minus 2i plus 3 plus 3i. So 5 minus 2i is a real number, a complex number, and 3 plus 3i is another complex number. We're adding two complex numbers. There's a plus sign between them. So it's kind of like combining like terms. So you add the real parts, which is 5 and 3, and you add the negative 2i and the 3i, that is the imaginary number parts. So you just add the 5 plus 3 and the negative 2 plus 3, so you end up with 8 plus I. And I'm looking at their work. Looks like they got an I on the end of 5 plus 3. Now, that should not be there. So that should be just 5 plus 3. They recorrected back at the bottom of the answer, making it 8 plus I, but there should not be an I after 5 plus 3. So it should be just 8 plus I. Okay? So you add the 5 and 3, you get 8, and you add the negative 2i and a plus 3i, and that's going to be just an I. So like negative 2x plus 3x is 1x. So therefore negative 2i plus 3i is 1i, and you don't need to put the 1. When you're subtracting them, it's the same idea. You just subtract their components. So what are the like components? Well, the 2 and the 12. So you subtract those. What's the other like component? Well, the 6i and the negative I. Those are like components. So we get 2 plus 6i. And they're going to distribute the minus. So it'll be a minus 12. And that becomes a plus I, because subtracting a negative I makes it a plus I. So now combining the like terms. So 2 and the negative 12. Notice I didn't put the I on this one. That was good. So 2 take away 12 and 6i plus I. So 2 minus 12 is negative 10. And 6i plus 1i is 7i. So like I said, it's just combining like terms. So on part A, when you add them, you don't have to worry about changing any signs. But on the B, when you're subtracting, you guys change the signs on the second expression. But notice your answer is a complex number as well. All right? All right, so look at example 2, and we're multiplying. Find the product. So 7i times 2 minus 9i, and we got 5 plus 4i times 6 minus 7i. Now, part A is definitely the easiest of the two, because here we're just multiplying an imaginary number, so it doesn't have the A part of it. So the imaginary 7i times a complex number, 2 minus 9i. So if you remember, when you have one term on the outside and there's two terms on the inside, how do you multiply that out? If you said distributed property, you'd be correct, and that's exactly what you do here. You take the 7i and multiply it by the 2, and you take the 7i and multiply it by the negative 9i. So if you multiply 7i times 2, you'll get 14i. 7 times 2 is 14. And then 7i times a negative 9i is a negative. Positive times a negative is a negative. And then 7 times 9 is 63. And then I times I is I squared. But remember, when we defined I as being the square root of a negative 1, I squared can be replaced with a negative 1. And that is the biggest problem students have with complex numbers right there. Okay? They don't know what to do with the I squared. They do not remember what that equals to. So I squared equals negative 1, because I is equal to the square root of negative 1. If you square both sides, I squared has to be negative 1. So you make that replacement. So I squared is negative 1. So the next step would be multiplying negative 63 times negative 1, which is a plus 63. And now we just want to put it in the a plus bi form. So the real number will go first. So that's why they placed the 63 to the left and then 14i to the right. So it's always in the form of a plus bi. And you might think, well, does that mean 14i plus 63 is wrong? Well, it's not wrong. It's just not in the correct form. Okay, so it's kind of like saying if somebody was trying to solve an equation and you put 1/2 and the answer is supposed to be written as a decimal and you write 1/2, it's not in the right form, or the form that somebody's requesting you to put it in. And so therefore the answer 1/2 and negative 0.5, although they're the same, it's not in the right format. So you might get a point taken off for that. So that's all. And that's just kind of cleanup stuff. So 63 goes first because the real number goes first, and plus 14i. It's all in the form of a plus bi. So let's look at the other one. And if you remember, when you're multiplying polynomials, two binomials, one thing that would come to mind, you might start thinking, oh, FOIL, this is what you got to do. It's first, outside, inside, last. Now, by the way, first, outside, inside, last is just a fancy way of saying distribute twice. So in other words, on part A, you had to distribute the 7i. On this one, you distribute the 5 through the other side, and you distribute the 4i to the other side. What that turns out to be is FOIL. Because when you multiply the 5 times the 6, that's the F, and then when you multiply the 5 times the negative 7i, that's the L. When you multiply the 4i times the 6, that is the inner, the I. And then when you multiply the 4i times the negative 7i, that is the last. So that's the L. So first, outer, inner, last. Okay, so that's how that works. So let's do it. Let's look at that. So you multiply the 5 times the 6. That's going to be 30 in a minute. And then multiply the 5 times the negative 7i. That's going to be the outer. So then you multiply the 4i times the 6. That's the inner terms. And then the 4i times the negative 7i, and that's the last terms. Okay, so it's just like FOIL when you were doing that in the course before this. So 5 times 6, of course, is 30. 5 times negative 7i is a negative 35i. 4 times 6 is 20. 4i times 6 is 24i. And then 4i times a negative 7i is a negative 28i squared. But here's that replacement. Remember, I squared is negative 1. So you make that replacement. So whenever time you see an I squared, it's a real number. Basically, bottom line is because the I squared ends up being negative 1, which makes it real again. So 28 times negative 1 is negative 28. Negative 28 times negative 1 is a plus 20 because there's a negative outside. And then you had a 30, remember, and that's going to end up being 58. So the A, the real part of this complex number, is 58. Now you're like, where does the negative 11i come from? That's just by combining the two terms in the middle. Negative 35i plus 24i happens to be negative 11i, and there's nothing else to do with that. So there's no other i's, just i's in the expression. So the final answer is going to be 58 minus 11i. So this is kind of old news, and there's only one little new part. It's still FOIL. The only new thing is that you got to remember what to do with the I squared. Because a lot of people, when they're doing this, the final answer would end up being 30 minus 11i minus 28i squared. So they end up with 3 terms. And it's because they don't know what to do with that I squared. So your goal or your job is to write that down in your notes. And remember, you should be doing notes. In your notes, you need to put down what the I squared equals to. Okay? Never leave the expression with an I squared. Never. Okay? Because that is a real number. Alrighty? So conjugate of a complex number. For the complex number a plus bi, we define its complex conjugate as a minus bi. Okay? So the reason a lot of people think of the conjugate as the opposite, and they're not opposites. Okay? A plus bi, the opposite of a plus bi is going to be negative a minus bi. That's the opposite. The conjugate is only the opposite of the imaginary term, the bi. So a plus bi, remember a is real, bi is the imaginary number part of that complex number. The conjugate is only the opposite of the imaginary part of it. The real part of it stays the same. Okay? And it says the product of a complex number and its conjugate is a real number. So let's look at that. Why is that true? Now remember, a and b are real numbers, right? It's only the imaginary unit, I, okay, that's the square root of a negative 1. So if you multiply the imaginary unit times b, which is a real number, you get the imaginary number. But by themselves, a and b are real. Okay? If you don't include the I, then the a and the b are real numbers. Alrighty? So let's multiply this out. So remember, we FOIL again. So what's a times a? And then a times a negative bi, and a times a positive bi, and then bi times negative bi. So it's just a FOIL. Okay? So a times a is a squared, and then a times a negative bi is negative abi, and then bi times a is a positive abi. You're like, why did they do it that way? They kind of like put the real numbers in alphabetical order. Okay, AB, and then the I at the end. So it's just a format, and it's easier to see that the two middle terms will cancel. Negative ABI plus ABI will cancel on the next step, and you'll see that when we get there. And then BI times negative BI is a negative b squared. I times I is I squared. But remember, I squared can be replaced with negative 1. So negative b squared times I squared is going to be ends up being negative b squared times negative 1, which is a plus b squared. And that a squared just kind of falls down from one step to the next. So the final answer is going to be a squared plus b squared. But notice, no i's. The imaginary unit was canceled out in the middle on that third step. So there is no other imaginary units. So, and remember, a and b are real. So therefore, a squared plus b squared is real. So we've proven that. But not only that, you've also proven something else. It's something else that's kind of nice. If you multiply two complex numbers that are conjugates, the result is always the sum of the squares of the real parts. So in this case, a squared plus b squared. Alrighty? So in other words, if you're going to multiply like 5 plus 4i times 5 minus 4i, this formula shows you that well, if you have 5 plus 4i times 5 minus 4i, then the answer will always be just the square of the two numbers, and it'd be 5 squared plus 4 squared. 5 squared is 25, 4 squared is 16, and add them up and you get 41. So if you're going to multiply 5 plus 4i times 5 minus 4i, the answer is 41. So it's very easy to figure out what that product is by this little proof here, if you will. Okay? Now the division. That's the hard one. Okay, and there is a reason why we talked about the conjugates there, guys, right in that previous slide, because in order to divide two complex numbers, you have to invoke conjugates. That's why it was there in the previous slide, is so we can do the division. Okay? So the goal of complex number division is to obtain a real number in the denominator. We multiply the numerator and the denominator of a complex number quotient by the conjugate of the denominator to obtain that real number. Remember, a squared plus b squared was the result, so it will be a real number. So let's look at an example. So using complex conjugates to divide a complex number. So 5 plus 4i is a complex number, and 4 minus i is a complex number. So we're going to divide them out. And a lot of people, this is probably the hardest of the operations, because when you're adding complex numbers, it's just adding components. Subtracting is just subtract the components. Multiplication is FOIL, and all you got to do is really remember is the I squared, what I squared equals to. So those three are in a little different class of easiness compared to this one. Okay, but a lot of people don't know how to divide, and so what they'll do is they just divide the components, and that's the biggest mistake people make. Okay, you cannot divide 5 into 4. You cannot divide the 4i and the negative i individually. Okay, so you can't just cancel out those things because they're not factors. So you got to follow the rules, and the rule is to multiply the top and the bottom by the conjugate of the denominator. Well, what is the denominator? Oh, it's 4 minus i. Well, what's the conjugate of the denominator? Oh, it's 4 plus I. So the next step is to multiply the top and the bottom by 4 plus I. Now remember, when you multiply 4 minus I times 4 plus I on the bottom, you end up with a real number, which we showed on the previous slide. The hardest part probably is going to be just being able to multiply those two numbers, 5 plus 4i times 4 plus I. But so we're going to have to invoke multiplication on both of these technically again. So if you look at the top, 5 times 4 is 20. That's where the 20 comes from. And then the 5i, the second term in the top, comes from multiplying the first and the last. So 5 times I is 5i. Where does the 16i comes from? Well, multiply 4i times 4, and you'll get 16i. Excuse me. Where does the 4i squared come from? Oh, that's multiplying the 4i times the i, the last terms in the complex numbers. So it's going to be 4i squared. Now the bottom, you FOIL that one out. That's going to remember the result will be a real number. Look what happens. 4 times 4 is 16. 4 times I is going to be 4i. Negative I times 4 is a negative 4i. Hence they're going to cancel out. And then I times negative I is a negative I squared. So looking at the top, if you remember, I squared is negative 1. So they replaced that last term with a negative 4 because you get 4 times negative 1, which is negative 4. On the bottom, the i's cancel, leaving you with 16 minus I squared, but I squared, remember, is negative 1. So that's going to be 16 minus a negative 1. And as you know, that's going to be 17. But if you remember from the previous slide, when I multiplied those conjugates, you can almost do it in your head. What's 4 squared? 16. What is 1 squared? Because that is the number in front of the I is 1. And what is 1 squared? 1. 16 plus 1 is 17. So you can almost do that one in your head. So we get 16 plus 21i. Why 16? Because 20 plus negative 4 is 16. And then 21i just comes down. Now remember, the bottom number is 17 because 16 take away negative 1 turns out to be 17. Now this one is technically the answer, but we don't like it in that form because we always want to put it in the a plus bi form. So we want to separate the imaginary part to the real part. So even though, if this didn't deal with the complex numbers, this answer would have been fine. But we always want to separate the imaginary part with the real part. Well, what's the real part? Well, the real part is 16 over 7. The imaginary part is 21 over 7. I'm sorry, 17. 16 over 17, that's the real part. And then 21 over 17i is the imaginary part. So technically what I have on the screen here is correct. It's just not in the correct format. So you might lose a point if you leave it this way. So in standard form, we'll write it as 16 over 17, that's the A, and then 21 over 17, which is the B, and then the I attached. So that last part is just a minor thing. It would be worth 1 point at the most, okay? But you don't want to lose those single points because they kind of combine and add up after a while, okay? So you might want to, on that previous slide, you might want to remember that, put that in your notes to always express your answers in complex numbers in a plus bi. Never leave anything attached. So you want to distinguish that. So, alrighty. Now, the principal square root of negative numbers. So for any positive real number b, the principal square root of a negative number, negative b, is defined to be this. So the square root of negative b is going to be I. Why? Because negative b is negative 1 times b. And the square root of negative 1 we know to be I. And the square root of b is whatever that is. Okay? So there's really nothing new here. So example 4, operations involving square roots of negative numbers. So perform the indicated operations and write the result in standard form. All right. So we're going to multiply the square root of negative 27. Okay, not multiply. We're going to add square root of negative 27 plus the square root of a negative 48, and we'll talk about b in a second. Okay. So remember that negative gives me an I on the outside. We have to take the square root of 27. Well, square root of 27 is 9 times 3. So the square root of 9 is 3, so that's why the 3 is on the outside. So 27 is 9 times 3, and 9 is a perfect square, so the square root of 9 is 3. So that square root of a negative 27 is 3i root 3. Now negative 48, square root of negative 48, there's that I coming out, and 48 is 16 times 3. And the square root of 16 is 4, that's why there's a 4 attached to that term. And the square root of 3 is on the inside. So the square root of a negative 48 turns out to be 4i root 3. Okay, because 48 can be broken down to 16 times 3. Now I have two terms that are the same. I root 3 to be exact. So we have 3i root 3 plus 4i root 3. This is like saying I have 3 apples, I'm going to add 4 apples to it. That's 7 apples. I root 3 is the apple. Okay, so 3i root 3 plus 4i root 3 is 7i root 3. Done. Okay, now if you notice, some people ask, well, why are you putting the I in the middle? Why don't you have the I at the end like it always has been? And you can, and there's nothing wrong with that. It's very simple why people shouldn't do this. Put the radical kind of in the middle, like for example, put 7 root 3i. Because if you do, and you make that radical symbol, and a lot of times we're going so fast that it looks like the radical is surpassing over the I. So they end up, it looks like 7 square root of 3i, and the I is inside the radical. And it's because you're being sloppy and making that radical symbol extend farther than what it should. So, and that would be wrong, because then if you have the square root of an I, it's actually the fourth root of negative 1. Okay, and that's not what I is. Okay, it's the square root of a negative 1. So the reason the square root of 3 is at the end instead of in the middle is to keep from making that mistake. Okay, so that's the only reason people do that. So that's why it's shown at like that. But if you can write a 7 root 3 I, as long as you're very careful not to extend that radical symbol over the I. Okay? Now the next one is negative 2 minus the square root of a negative 3 squared. So the first thing you would do is take the negative out. So you have a negative 2 minus I root 3 squared. And then you square it, so you FOIL the same thing out. So you don't put the square on the inside. You don't just say negative 2 squared and I root 3 squared. Okay? You don't bring the squared inside. You have to multiply the same binomial times itself, which is going to be totally different because you're going to have to FOIL. So negative 2 times negative 2 is 4. That's where the 4 comes from. And then negative 2 times negative I root 3 is going to be a negative 2I root 3. When you multiply the two terms in the middle, you get the same thing. Negative 2 times negative I root 3 is going to be plus 2I root 3. So actually there's a plus. So it's going to be plus 2I root 3 plus 2I root 3 because you're multiplying two negative numbers together. Then you get negative I times negative I, which is going to be an I squared. And then root 3 times root 3 is root 9, which is 3. So that's why there's a 3I squared at the end. It's because negative times a negative is a positive. That's why it's plus. I times I is I squared. And then square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is 3. Okay, so that's why it's 3I at the end. Then you start looking at the I squares. Well, the 3I squared it's going to be a 3 times negative 1. So I'm at the second to the last step. So 3 times I squared, it'd be 3 times negative 1. And then we got 2I root 3 plus 2I root 3 is going to be 4I root 3. Because it's adding 2 apples plus 2 apples. And the apple being I root 3. Okay, and then we got the 4 at the very end, at the very beginning. So 3 times negative 1, remember, is negative 3. To add to 4, and you'll get the 1. That's why there's a 1 at the very beginning at the last step. 4 plus negative 3, basically, and that's 1. And then bring the 4I root 3 straight down, and there's your answer. 1 plus 4I root 3. Now notice again, that radical is at the end of it, but you could also express it as 1 plus 4 root 3I. Okay? I don't put it on my key that way. I accept it when students do it that way, and that's fine. As long as, like I said, as long as that radical doesn't extend past or over the I. You just have to be very neat when you're doing it that way. Okay? So if you don't think you can write very neatly and make sure that radical doesn't extend over that I, then don't make me guess either. I'm like, okay, is that radical symbol over the I? You got almost to it, but it's not quite there, or it is right, just barely touching it. You usually don't get the benefit of the doubt on that. Okay, so make sure if you do it, make sure you stop that radical way before you get to and write that before you write down the I. Okay, all right. Next one, okay, quadratic equations with complex imaginary solutions. Now, we've already discussed in back in the prereq section about the quadratic formula. We've already discussed the quadratic formula at this point already, but if you remember back in those, when we were doing that section, every time we did it, we got a real number. We were not talking about imaginary units. So every number that you had, or every solutions you had, and then back in, it was actually, I think it was P7, that was the prereq 7 section that we did earlier in the course. When we did that, all your solutions were real. None of them had imaginary answers or complex answers either. So this section, this is where it changes. We're now going to start getting with complex solutions. So a quadratic equation may be expressed in the general form ax squared plus bx plus c equals 0 and solved by the quadratic formula x is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Again, something that we've already discussed in P7. We've had this formula. This is just a second run around of this formula, and it's just a matter of what kind of solutions we're getting. Now, before the discriminant, b squared minus 4ac, and it's called the discriminant, and if the discriminant was negative, the quadratic equation has no real solutions, means they're going to be complex. So when you have solutions to these equations, your solutions are either going to be real or complex, one or the other. Okay, so back in P7, they were real. Okay, now here in 2.1, they're most likely going to be complex. Okay, so when we come to test time, you may get both, and you don't know which one it is. So you're going to end up trying to use the quadratic formula. This first problem might be a complex answer, and the next problem might be a real answer, based on what the discriminant is. The discriminant is what's inside the radical. B squared minus 4a is located inside the radical. And if it's positive, we're going to get real answers. If it's negative, which I'm most likely that's what's going to happen in my example, they're going to be complex. So if they're negative, they're complex. If it's positive, it's real. Bottom line. Okay? If the discriminant is negative, the quadratic equation has no real solutions. The quadratic equation with negative discriminants have two solutions that are complex conjugates. That's important, leading up to some other things that we're going to be doing later in this chapter. Okay? And the next chapter as well. So what I'm saying is, if you have a quadratic equation or a polynomial equation where a plus bi is a solution, then a minus bi is also a solution. So if I told you that 5 plus 3i is a solution to this quadratic equation, then you're guaranteed you know the other equation's solution, the other solution to the equation, which is 5 minus 3i. They come in conjugate, what we call conjugate pairs. Okay? So that's the beauty of this. Okay? So if you know one, then you have to know the other. Okay? All right. So example 5, a quadratic equation with imaginary solutions. So we're going to solve the equation x squared minus 2x plus 2 equals 0. So if you notice, it doesn't factor. Okay? You can't find two numbers that'll multiply, give you 2, and then combine to give you negative 2. That's not going to happen. Okay? So you couldn't factor it even if you wanted to. Alrighty? Now, if it factors, do you have to use the quadratic formula? Well, it kind of depends on what's being asked. If they tell you to use the quadratic formula and it factors, you have to use the quadratic formula anyway. If they say solve the equation and they don't tell you how, it's your choice. Okay, but this one doesn't even factor, so you're kind of left with the quadratic formula. Okay, so before I start writing that, can you look at the equation and tell me what the a, the b, and the c are? What are those numbers? If you said a is 1, b is negative 2, and c is positive 2, you will be correct. Okay, so a is 1, b is negative 2, c is positive 2. Now, so x is opposite b, plus or minus the square root of b squared minus 4ac all over 2a. So they put the b in. Remember, b is negative 2, so that's why it's 2 at the very front now, because it's negative b and b is negative 2, so that's why it's 2 plus or minus the square root of b squared, which b is negative 2, so it's going to be negative 2 squared, minus 4 times a is 1, remember, and c is positive 2, all over 2 times 1, because it's 2 times a, and a is 1. Okay, so we got 2 plus or minus 4 minus 8, square root of 4 minus 8. Why is it for square root of 4 minus 8? Well, remember, negative 2 squared is 4, and 4 times 1 times 2 is 8. So I'm actually trying to calculate the discriminant is what I'm doing, all over 2. So it's going to be 2, again, plus or minus the square root of a negative 4, because 4 minus 8 is negative 4, and that's all over 2 times 1, which is 2. So I get square root of a negative 4, but what's the square root of negative 4? 2i. Okay? So it's going to be 2 plus or minus 2i divided by 2. So the quadratic formula is really nice as long as you know the formula. You can't. The formula is not one of those things you can be close at. Well, I wrote down the quadratic formula, but I have b squared plus 4ac in the discriminant. I had everything right on the formula, but I put a plus instead of a minus 4ac. Plus, close doesn't count here, okay? You have to be exact. The formula doesn't work otherwise. You have to be exact on the formula. So, putting a b squared plus 4ac as the discriminant is next to not even knowing the formula at all, which is unfortunate, okay? So anyway, we got 2 plus 2i divided by 2. So we tried it, well, what I would have done was just divide 2 by 2 and got 1 plus or minus, and then 2i divided by 2 is I. So it's 1 plus or minus I. So what are the solutions? It's 1 plus I, that's one of them, and it is a complex number. And the other solution is 1 minus I, that's another complex number. But more importantly, look at what kind of numbers they are, other than they're complex. They're conjugates. One is 1 plus I, and the other one is 1 minus I. So in the original formula, in the quadratic formula, you got a negative b plus or minus right there. That is a guarantee that you're going to have conjugates. Okay, so a plus bi and a minus bi. That's the guarantee that there will be conjugates. So the solutions are complex conjugates. The solution is 1 plus I and 1 minus I. Now on a test, I don't really care how you write it as 1 plus I and 1 minus I plus or minus. It really doesn't matter, but I will tell you in my math lab where you'll be doing your homework at, they will not allow you to use 1 plus or minus I. They're going to be saying to you to write them in comma format. Basically, they want you to write it as they have it up there, 1 plus I, comma, and then 1 minus I. A lot of times that's what they'll do. So be very careful of how they say to express your answer. You can know everything, how to do the problem mathematically, but if you're giving it to them in the wrong format, they won't give you credit for it. Okay, so it's very important that you're reading my math. I'm a little bit more flexible on exams, I'm a little bit more flexible on exams, but on my math lab, they're very, very particular how you write the solutions. And because you got to remember, they're asking you to put the answer down, but they're comparing your answer to what they have in the database. Well, the 1 plus or minus I is not in their database. And so when you write that down, it goes to the database. That's not it, that's not it, that's not it, that's not it. And so it doesn't give you credit for it, even though technically you'd be correct. So be very particular, be very careful of how you express your answer. Make sure you write it the way they want you to write it. Okay? It's non-negotiable. Okay? So, alrighty. So I hope you're taking notes. You took notes to this. And if you didn't, it'd be a good time to go back and just redo the video down. At least write the examples down, guys. At least put down the examples that I'm doing here, and put that in your notes as well. The examples is very important that you know how to do those types of problems here. Okay, writing all the other stuff like the definitions and the concepts, that would be great as well. Okay, but minimally you need to be putting the examples in there. Okay, on your notes. So that way you don't have to go watch the video 12 times when you're studying for the exam. You can just look at your notes. Okay, so anyway, I know you're getting tired of hearing me say that, but you're going to hear it anyway, and because I want you to be successful in the class, and I believe that's what my belief is. That's one of the ways to be successful is to write notes, because it goes from pencil to brain better than just visual. So, all right, and as always, if you have any questions, feel free to contact me via email. Okay, and I can answer some of your questions at that point. Okay, like I said, these videos don't show every type of example that you'll ever encounter, so that's why that's the email. That's why this is open for you to access. Okay, all right. You have a good day. See you in the next section. Take care.